Shown below is a circuit containing a resistor network. Let the values of the labeled components be as follows. R1 is 2 kiloohms, R2 is 3 kiloohms, R3 is 4 kiloohms, R4 is 6, and the voltage is 10 volts. We are to find the equivalent resistance of the network and determine the current, voltage, and power dissipated by each resistor. In this problem, we recognize that we are analyzing a resistor network, and we also know that the simplest way to analyze this is to do so in the form of a table. Because the equation that governs simple resistors is V equals IR, the table will contain these three quantities as the headings. We'll list them as resistance, voltage, and current. Finally, since this problem also asks us to calculate the power dissipated in each resistor, we'll make one extra column to this table, the power column. This column will not be used while calculating the network's characteristics, but instead it will be merely calculated sort of as an afterthought. The table begins with 4 rows for the resistors 1, 2, 3, and 4. And throughout the process of filling in the table, we will, as necessary, dedicate rows to equivalent resistors, and just for clarity, we'll label those as A, B, C, D. The first step in simplifying the problem is to recognize that resistors R2 and R3 are in parallel with one another and can be replaced by an equivalent resistor RA, yielding the circuit shown here. R1 is in series with RA, and that pair is in parallel with R4, and I've left out the battery to make the diagram as clear as possible. The next level of simplification is to combine resistors R1 and RA in series into a new equivalent resistor, and we're going to call that one RB. Finally, the last simplification is to combine resistors RB and R4 in parallel, making resistor RC, and then in this diagram we finally put back the battery in its original orientation, because now the circuit is simply one battery and one resistor, and the value of the battery is still 10 volts. We now see that the completion of the analysis is going to involve 3 additional rows, RA, RB, and RC, and our job is to calculate all the appropriate values. First, let's fill in the given set. Here we've chosen to express the resistors in ohms. You could also do this problem by expressing the resistors in kiloohms. We recognize that RA is made out of the parallel combination of R2 and R3. R2 is 3 kiloohm and R3 is 4 kiloohm. If we put 2 3 kiloohm resistors in parallel, then we would get 1.5 as our answer. If we put 2 4 kiloohm resistors in parallel, we'd get 2 as our answer. Our answer must be between 1.5 and 2 kiloohms, and if we use the appropriate formula, 1 over R total is 1 over R1 plus 1 over R2, we come up with the result 1714, which is exactly as we would expect. Next we see that RB is made out of a series combination of RA and R1. In series, we add the resistances to get the total, so adding 2 kiloohms to the 1714, we come up with 3,714 ohms. Finally, RC is the parallel combination of RB and R4. The answer we anticipate in advance must be somewhere between half of RB and half of R4, and when we perform our calculation, we find that the result is 2,294 ohms, and this is indeed larger than half of RB and smaller than half of R4, indicating that we probably did the calculation correctly. Now that the circuit is simplified down to a single resistor on a single battery, we recognize that the voltage applied to RC is 10 volts. Anytime we have 2 out of the 3 of the combination of R, V, and I, we can use Ohm's law to find the third one. In this case, we can solve for I is V over R. In order to make the table as compact as possible, we're going to choose to express the currents in milliamps rather than in amperes, and that will save us a little bit of leading zeros beyond the decimal point. The result for resistor RC is that the current through it is 4.36 milliamps. Now we begin the process of taking apart our equivalent resistors into their individual elements in order to learn everything about every device in the entire circuit. RC was made of the parallel combination of RB and R4, and we recognize that for devices in parallel, all of them will always have the same voltage, meaning that RB and R4 will both have 10 volts. We now have two lines with 2 out of 3 quantities calculated, so we can simply finish the calculation using Ohm's law to yield 2.69 milliamps for RB and 1.67 milliamps for R4. At this point, because we want to get 100% credit on the problem, we choose to invoke our checksum. Indeed, since the voltages were equal on the two components, the currents must sum to the total, and if we take the 1.67 and add the 2.69, we do get 4.36, meaning we can trust our calculations so far. Now let's take apart resistor RB. Resistor RB was the series combination of R1 and RA, and we recognize that for any elements in series, the current is the same for all of these elements, so we'll have 2.69 milliamps in both RA and in R1. We notice that on both the RA and the R1 lines, we have 2 out of the 3 V equals IR, and so we're able to calculate the third, which is the voltage. Our results of 4.61 and 5.38 do indeed add up to 10 as the total voltage, and so our checksum continues to work. We're down to one final step of disassembly, and that is we will disassemble resistor RA into R2 and R3. Because these are made from a parallel combination, we will copy the voltage of 4.61 volts into each of those rows. 2 out of 3 on these rows allows us to calculate the currents, and these two calculations yield 1.54 milliamps and 1.15 milliamps. Once again, invoking our checksum, we do see that 1.54 plus 1.15 milliamps adds up to the 2.69 milliamps, which is the total for RA, and so we believe that the calculation is entirely correct up to this point. As the final afterthought to this calculation, we'll be calculating the power. P is V times I. And since every row has an entry for both V and I, we're able to simply multiply these. For compactness, since we are multiplying volts by milliamps, our results will be in milliwatts. And so, for the 4 physical resistors, we have 14.5, 7.1, 5.3, and 16.7 milliwatts. And just for fun, calculating the power in resistor RC, we get 43.6, which indeed is consistent with the sum of the 4 physical resistors.